Kids, sorry to be out again today. I'm at another county meeting. Woohoo! Hopefully you have been given the warm-up handout where you're trying to find a pattern with I's, knowing what we learned with I yesterday. So you can pause the video and wait if you like. Don't forget we have a quiz on Tuesday, and today would be the last topic. New topic that would be on the quiz on Tuesday. Everything from, just the quiz is only on the stuff we've done since we got back. So just discriminant and work and complex numbers and all that we've done yesterday and that we're going to do today with complex numbers. So with that in mind, if you notice the given parts that I told you, that I gave you on the front of this handout, right, where at the top of this, right, I know this part is second, but before this, I have what I to the 0. What is anything to the 0 power is? 1, right? What is anything to the first power? Itself. From yesterday, what did I tell you by definition? What is I squared? Right? And then using my exponent rules, if you see what I wrote out there, I can take I cubed and I can rewrite it as I squared times I to the first, right? So I'm using two previous answers, but I squared is -1 times I, which is -I. Now I want you to notice that that is 1, or 0, 1, 2, and 3. So using this same thinking, what would you do here with I to the 4th? I could write I to the 4th a bunch of different ways. I could write it as I cubed times I to the 1st, right? But what is I cubed? You just found out I cubed was -I. And then, of course, you have times I, so I have -I squared. But what is that? -1, but that is 1. How about I to the 5th? Well, that is I to the 4th times I to the 1st. But I to the 4th, we just found out was 1 times I, which is I. I to the 6th is I to the 5th, which we just found out, times I. I to the 5th was I times I, which is I squared, but I squared is -1. I to the 7th is I to the 6th times I to the 1st, which is the -1 from the previous step, times I, which is -I. Now, remember I'm looking for a pattern here, right? What do you think here? Look how I've lined this stuff up. I to the 4th is the same answer as I to the 0. I to the 5th is the same result as I to the 1st. I to the 6th is the same result as I squared, and I to the 7th is the same result as I cubed. Says this little frog. Let's go down to I to the 8th. I to the 8th is I to the 7th times I. I to the 7th is -I times I. Hey, I've seen this movie before. That's -I squared, but I squared is -1. What is -1? 1. I think I've seen this movie before. What is what do you predict I to the 9th will be? And I to the 10th, and I to the 11th. Can you write a rule then for simplifying I to any number as long as that exponent n is a positive integer. Remember, that's what z to the plus means, right? Positive integer. Well, let's see. Each one of these is a chunk of what? Each one of these groups seems like the pattern repeats every what? 4. What happens when you take for instance, a number like 12 and divide it by 4? What do you get? Actually, you get I don't care. What's the remainder? What happens when you take a number like 13 and divide by 4? You get I don't actually care, but what's the remainder? How about 14? I don't care, remainder. How about 15? I don't care, remainder. Are you ever going to get a remainder of 4 when you divide by 4? I think not. So, what does this mean? If you take, right, what do you suppose then I to the 12th is? I to the 12th is going to be the same as I to the remainder of 12 after it's divided by 4. And I to the 0 is 1. What is I to the 13th going to be? It's going to be the same as I to the remainder when you divide 13 by what? 4. How about I to the 19th? I to the 19th is the same as I to the remainder when divided by 4. And how about I, 13, that's a 14. I said 19, didn't I? 14. How about I to the 15th is going to be the same as I to the remainder when I divide by 4. So hopefully the lesson learned here is that your rule is I to the n will always equal I to the remainder of n divided by 4. Right? That's all up in exponential land. And so you're always going to get that, but these answers will always be I to the remainder 0, I to the remainder 1, I to the remainder 2, and I to the remainder 3. And you've memorized those ones. You do need to memorize those results. I to the 0 is 1, I to the first is just I squared is -1, and I cubed is -I. Crazy, right? So try these. Turn your paper over and your warm-up paper over and put these on them. Pause the video and then see if you get what I get. So I take the exponent 23, divide it by 4, and get I don't care 5. But the remainder is 3. Right? I don't care about that 5. You do actually have to know how to divide and what remainders are, right? It's the 3 I care about. So notice what I'm going to do with that remainder. Whee! Turn that 23 into an I cubed, and hopefully you've memorized what I cubed is. Oops, sorry. Right? I cubed is -I. So how about 101? So this is technically I to the remainder of 101 divided by 4. Oh crap, I forgot. I don't know what that is. And I don't have a calculator. Plus a calculator gives you decimals, dippies. So 4 into 101. 4 goes into 10 twice. 4 goes into 21 5 times. Don't actually care what's my remainder. So this turns into I to the first, which equals I. Hello, I to the 40. What is that divided by 4? Don't care. What's the remainder? 40 is divisible by 4, so this turns into I to the what? What's the remainder when you divide? And then what's I to the 0? 734. Oh no, I don't know what 4 divided by. Well, okay. So 4 goes into 7 once. 4. Subtract. 4 goes into 33. 8. 32. Subtract. 4 goes into 14. 3. 12. What's the remainder? So I to the 731st is equal to I squared, which is -1. Now remember, I taught you yesterday that there's an I button on your calculator. Well, go ahead. You can type in I squared and it'll give you -1. But try to put in I to the 101. Try to put in I to the 40. Try to even put in I to the, I don't know, 19th or something. Your calculator can't quite handle those. It freaks out. You need to be able to tell me what I to the any positive integer is by using the rule of the remainder after dividing by 4. All right. Make sure you write on the top of this warm-up, this simplifying i's using this pattern will be on the quiz on Tuesday. So will dividing. Now remember, the dividing is in quotes because, as I told you yesterday, you don't really divide in complex numbers. So I'll show you what I mean by that. I want to remind you that yesterday, so this should be in your notes now. Yesterday we ended the lesson with special cases of multiply. Special case 1 was squaring a complex number. And so anything you want. What do you want? Let's do 3 minus, I don't know what, 7i, let's say. Using my Algebra 1 knowledge, I know that's going to be 9 minus 21 doubled plus 49i squared. But you are supposed to recognize that I squared will turn this into -49. And then you are supposed to put the 9 and 49 together. And remember, a complex number is of the form a plus or minus bi. So a in this case is -40. And b you can either think of, if you're doing plus, it would be -42i, or if it's minus 42. Right? Either way. Remember, the other special case was taking 3 minus 7i and multiplying it times 3 plus 7i. Multiplying these two complex numbers together, because remember, this is really just 3 minus 7i times 3 minus 7i, right? Multiply two complex numbers together and you get a complex number back. Complex times complex equals complex. However, yesterday we recalled another Algebra 1 pattern, that when you have these two terms that look exactly alike except for the signs, that what's going to happen is you're going to get 9 from 3 times 3, but then you're going to get -21i and +21i. That's going to cancel out. Then you're going to multiply the -7i plus the 7i, and you're going to get -49i squared. but that's 9 minus 49 times negative 1, which is 9 plus 49, which is 58, which is in the real numbers. So multiplying two special complex numbers gives you a real number. This is so special it has a name. Now in Algebra 1, you probably did not hear this language, but I used it with you. In Algebra 1, x plus 5 times x minus 5 gives you x squared minus 25. The middle terms drop out. These two binomials are called conjugates because they are exactly the same except for the plus and minus. In general then, if I had a plus b times a minus b, what does that turn into? These are conjugates, right? And when you multiply these conjugates together, what do you get? Right? Let's now go back to our complex conjugates. You see what I did there? See what I did there? Let's go back to complex conjugates. These are, because they're complex numbers, complex conjugates. So if I gave you 3 minus 7i, 3 plus 7i is its complex conjugate. And notice what happened. Can you tell me the complex conjugate pattern? If I had any a plus bi times any a minus bi, what is the pattern going to be? What is the result of that always going to be? And look at what happened here. A, B, A, and B. What did you end up with? Isn't 9a squared? And then instead of the minus in regular algebra with real numbers, because negative 7i and positive 7i is negative 49i squared, which resulted in this negative 1, I do have 49 is b squared, isn't it? But the I squared turns this negative into a positive. So the complex conjugate pattern, if you don't actually have to multiply them out, it's just a squared plus b squared. Let's do an example up here. Can you quickly tell me what the result would be if I have 2 minus 5i, well, let's do plus this time, because it doesn't matter, right? And 2 minus 5i. Multiply those together. What do you get? Firstly, you're going to get a real number. And that real number is going to be two squared and 5 squared, right? Because 2 is the a, 5 is the, and then what's going to happen in between? This is super helpful. And it's going to be super helpful for when we quote unquote divide. So, when you're dividing, there's a rule. And it's a rule I didn't make up. And it's really only a rule for convenience. But you have to follow the rule, unfortunately, even if you don't agree with it. Mostly because multiple choice answers are always presented this way. Only real numbers are allowed in the denominator. How you're going to get rid of any complex numbers is you're going to use your fraction knowledge. Fractions. you're going to use that I squared is a real number, and complex conjugates can get me to real numbers, right? If I'm in the set of complex numbers and I really, really, really want a real number, I squared is a real number, and complex conjugates can get me to a real number. So, example 1. 5 divided by 2i. You're not actually going to divide that, but you have to get rid of the I. The 2 is okay, leave the 2 alone. Just the I. Well, I don't have an equation. I have an expression. Guess what I can do to any expression? Multiply it by 1. I'm just going to be really clever about my 1. Guess how I'm going to write my 1? Oh, snap. I am multiplying a fraction by 1, so I do not change its value. Whoops, sorry. What do I get out of this? 5i. Now, I used to have a numerator that was real. Now I have an imaginary numerator. I have I in my numerator, but that's okay because what's in my denominator? 2i squared, but what is that? Right, you can put the negative in the denominator, you can put the negative in the numerator, or you can put the negative out front, right? Matters not. Okay, so that's not so bad. But look at this. So while you're copying this down, I want you to not do what I'm going to do. And I'm going to use my same thought process. I'm going to multiply by 1, which is legal, right? But in this case, it's not useful. Do you know why? Again, who cares what happens to the numerator? How did I get plus 2? How did I get plus 2? Oh, that's negative 2i squared, right? And negative 2i squared is negative negative 2, which is positive 2. What happens in my denominator? I got an I squared, which is a real number, but did I get only real numbers in my denominator? No. Sadness, madness. So what do you think I can do instead? Oh, somebody's at the door. Who is it? Come on in. Who's coming in? Oh, it's the complex conjugate. Come on in, complex conjugate. Oh, it still has to be a 1. What is the complex conjugate? To who? Who do I want the complex conjugate of? It ain't the numerator. It's the denominator. So I look at the denominator and say I need a complex conjugate to the denominator. So I copied A over, I copied B over, and I changed the sign in between. But remember, I still have to multiply by what? 1. So whatever I've written in the denominator, I have to copy over in the numerator. Now this is a slightly annoying problem at the top, but not in the bottom, because we just memorized our complex conjugate pattern. A squared, B, which by the way, what is B? 1 or negative 1, it doesn't matter, you're going to square it. What's the sign in the middle? A squared plus B squared. So my denominator is going to be 17. Now my numerator is going to be messy, right? Negative 12 minus 3i plus 8i plus 2i squared. So that's going to be negative 12 plus 5i minus 2. So that's negative 14 plus 5i over 17. Now you should try this on your calculator, right? In your calculator, type, make sure you use parentheses, 3 minus 2i divided by negative 4 plus I. And look at what you get. Looks kind of weird, doesn't it? Try to math fraction it. I don't know if math fraction works, but what you'll get is this. Negative 14 over 17 plus 5 over 17I, which is the same thing as negative 14 plus 5I over 17. Okay? Oh, wow. Okay, so we've basically taken care of 3 objectives today. Objective 1, that will be quizzed on Tuesday, is the I pattern. Objective 2, use I squared and complex conjugates, or C squared, to get rid of I in denominators. Objective 3. Solve this random looking quadratic that has no i's in it and check your solution. Now, why do you think I have this guy here? Yawn, this is Algebra 1. And you know what? When I was in Algebra 1, I was like, oh my gosh, don't make me check the answer, right? I don't want to check the answer because I know how to factor and I know that I'm going to get 2 solutions and I know that I did it right. Oh, but if you make me do it, I'm so annoyed, but I will if you give me, since you said it was worth some points. I will. Oh, snap. Somebody really is at the door. Hold on a second. Thank you. This is a UPS delivery, but now I have to sit here and not open these packages until I finish with my video. Oh! Who's it from? Ooh, something from one of my sons. And something from Target. Woo! Okay, anyway. All right, so I will check my answer because you made me. So let me check 5 first. 5 I'm going to replace for x, right? 5 squared minus 7 times 5 plus 10. Best equal what? You solved an equation that equals 0. So when I put 5 in for x, I got 25 minus 35 plus 10, which does in fact equal 0. Guess what happens when you put 2 in? Square it. Minus 7 times 2 plus 10. Shock of all shocks, what are you going to get? 4 minus 14 plus 10 is in fact 0. Duh. Well, the reason you practice this in Algebra 1 with easy integers and they make you check it is because the process stays the same, but the numbers get uglier. Oh, I forgot also on your calculator, here's what I want you to do. I want you to, I want you in your calculator in y1, I want you to put x squared minus 7x plus 10. Then on your home screen, I want you to type 5, store, and then hit alpha A. Then on your home screen, I want you to do the following. A squared minus 7a plus 10. Enter. What do you get? Woot! 0. So, of course you don't actually need to do that with 5 because 5 is such an easy number. But when numbers aren't so easy, we might want to use this store capability. So notice, and I'm going to go back, solve and check your solutions. When you are solving with no other directions, right? Whoops. Solve, right? What set are you supposed to assume? You're solving over the set of real numbers. Now look at these directions. I say the word solve is still there, and solve means make y equal to 0. You assume real numbers unless otherwise specified, and look what I did. Solve over the set of complex numbers. Remember, I could also just use the symbol, complex. Now, the solutions to these might be real, but if they're not real, I'm supposed to still find their solutions. So the first thing, of course, I try to do is factor. And I said x, and then I went, oh, dagger. Right? There were no factors of 26 that I could find to get to -10. So who comes to my rescue, right? When I can't factor into the set of rational numbers, the quadratic formula. So this is the answer I got with the quadratic formula, right? I did x is equal to -10 plus or minus the square root of b squared minus 4 times a times c. And I can already see that 100 minus 4 times more than 20 is going to be negative. In the set of real numbers, I stop, right? But I'm not in the set of real numbers. I'm over the set of complex numbers. So I ended up going x is equal to 10 plus or minus the square root of 100 minus 4 times 26. What do you get? 26 times 4. Right? 8, 9, 10, 104. So I get 100 minus 104 all over 2. X is equal to 10 plus or minus the square root of -4 over 2. This is why you did the homework last night. X is 10 plus or minus. Suck that negative out. Becomes an I times the square root of 4 over 2. Square root of 4 simplifies. 10 plus or minus 2i over 2. This is why it is useful for people to have made you simplify all along. You need to know that that is 10 over 2 plus or minus 2i over 2. And you don't have to know that, but my version, 5 plus or minus I, because 10 over 2 is equal to 5, and 2 over 2i reduces to 1i, is going to be easier for me to work with. Not in a final answer. If the question just said solve over the set of complex numbers, I'd probably leave my answer right here. But that's not the whole directions. I want you to check one of your solutions. To check one of my solutions, the 5 plus or, oh, how many solutions did I get, by the way? I got 2. Remember, my solutions are 5 plus I as well as 5 minus I. I only ask that you check one. Pick your favorite. Most people pick the positive one. We're just positive human race, right? Whoops, I'm sorry. So, to check that solution, here is your x. Go to the equation and plug x in. Which one do you want to use? I thought so. 5 plus I gets squared minus 10 times x plus 26. And if you've done your math right, what should that equal? 0. I'm going to do this one first. Negative 50 minus 10i, right? I just had to distribute because there was no exponent. This has an exponent. I need to square. Because I've done Algebra 1 over and over and over again, I can do this quickly. 25 plus 10i plus I squared. Now combine. What do I have here? Plus 10i and negative 10i are going to go away. What's I squared? Negative 1. So I have 25 and a negative 1 minus a 50 and a 26. So I have what? Positive 24, positive 26, negative 50. Shocker! What does that equal? Therefore, what must 5 plus I be? It's not an x-intercept, but it is a solution. Why is it a solution? Because I freaking plugged in for x, multiplied and squared and combined, and I did get equality. That's why it's a solution. Guess what would happen if you put in 5 minus I? Nuh-huh. So now, again, let's try go to your calculator. And in your calculator, now you have to change y1. Change y1 to that quadratic, right? And see what happens if you put in, oh, I'm sorry, you don't need to put it in to y1. I'm desperately trying to find my calculator. That's why you hear me rumbling around. Don't put that into y1. Matter of fact, I don't know why I did that originally. Aha! So, oh, I know why I did that, because I was going to show that if you put it in y1 and try to plug in a complex number, it will blow up on you. But if you do it on your home screen, so on your home screen, put 5 plus I on your home screen, just like I did when we did 5. See that planning there? 5 plus I, store that in alpha A. Then on your home screen, type A squared minus 10A plus 26 and see what you get. Oh, snap. What happened? Yep. Now, without doing the algebra, do 5 minus I and store that in alpha B. And do alpha B squared minus 10 alpha B plus 26. Guess what you get? Guess how many other numbers you can plug into x and generate 0? None. There are only 2 solutions. And the 2 solutions were 5 plus I and 5 minus I. They were not real, therefore this parabola does not cross the x-axis. But it still has 2 solutions. They're just not real solutions. And now we can not only find what those real solutions are, we can plug them back in to verify that they are solutions. So let's do another one. Let me get rid of all of this drawing here. Solve over the set of complex numbers. Check one of your solutions. So let me save you a little bit of time and tell you that that's what the quadratic formula will give you. And that's a little bit of a dagger, right? The last one was so nice. It simplified to 5 plus or minus I. This one does not. Don't panic. Don't panic. Just because the numbers are uglier, right? Excuse me. Here's my solutions, right? I did number 1, check. Now, to complete number 2, take one of those solutions, because that is 2 of them, and plug them back in. I think I might actually write this one as 3 halves plus or minus I root 155, which does not simplify over 2. So here's what I'm going to do. I'm going to take the positive one, 3 halves plus I root 155 over 2, and what are you going to do to that? Minus 3, just for emphasis sake, I'm going to make that 3 over 1 because I'm going to multiply it by 3 halves plus I root 155 over 2. And then I'm going to add 41. And if I do my algebra right, and I've done my quadratic formula right, what am I going to get? 0. So let's take care, just like we did the last time. I would do this part first. So I'm going to get negative 9 halves plus 3I root 155 over 2, right? Because when you multiply fractions, you just multiply the denominators. 1 times 2 is 2. 1 times 2 is 2. Multiply the 3 times the 3, that's where the 9 goes. Multiply the 3 times the I times the 155, and I get 3 times the I times root 155. This part, be careful with. Square. Square a binomial. Square 3 halves, and what you don't get 9 halves, what do you get? 9/4. Square this. What happens when you square root 155? You get 155, right? What happens when you square the denominator? You get 4. What happens when you square I? Right? But what about the middle terms, right? What do you do with the middle terms? You multiply them and double. So let me do that over here. What is 3 halves times I root 155 over 2? That's 3I root 155 over what? 4. Now, double that. What do you get? You get 3I root 155 over 2, right? And it was positive. Oh, and look, thought I made a mistake there. I did make a mistake. This is a negative 3 times this I root 155 over 2, so this has to be negative. Do you see what happens already? Bye-bye, eyes! Bye-bye! Positive 3I root 155 and a negative 3I root 155, both of them over 2, go away. So what do I have left? I have 9 over 4 minus 9, oh dagger, minus 9 over 2. Hey, isn't that 18 over 4, right? Times 2 times 2. So check, check, and then minus 155 over 4 plus 41 times 4 over 4, right? What is that? Nine minus 18 is -9. -9 minus 155 is -164 over 4 plus, what is 41 times 4? Oh, snap! 0 does equal 0, therefore, what must be true? 3/2 plus I root 155 over 2 is a solution. Not an x-intercept, because x-intercepts by definition must be real, but 3/2, this complex number, is a solution, will generate 0 to this quadratic. What's the other solution? And if you don't believe me, you can check this on your calculator by doing just what we did with 5 plus I. You do 3 plus I root 155 all divided by 2 and store that in alpha A. Sweet! All right, so that's the end. Pick up, you have a homework worksheet, right? And the homework, and I'm going to check, remember the Thursday homework and this Friday's homework on Monday. And if you look at the complex worksheet number 2, there's 3 examples like we just, right, of solving over the set of complex numbers and checking one answer. But if you look at number 3 and look at this problem, well, they're the same. So you've really done number 3 in your notes. I suggest doing it again since it's got fractions. Number 4 is just solve over the set of complex numbers. You don't have to check your answer. That's just has some nastier numbers, getting you to work and simplify with the quadratic formula when it's a little nastier. 5 and 6 are reference discriminant work that we did, so those are nice questions to look at as review for the quiz on Tuesday. And then 7 through 15 are all working with i's, the stuff we did today, right? The quote-unquote divide, where you are just getting rid of I in a denominator, either with I squared or with complex conjugates. And there's also some problems with the I patterns, the 11, 10, 13, 11, 14, 12, and 15, right? 7, 8, and 9 are 7, 8, 9 are the divide ones, okay? All right. I hope you have a great weekend working with these complex numbers. I know it was probably crunchy for you to get the Cheerios in today, but I didn't want you to have to worry about it over the weekend. So have a great day and weekend. Have a great weekend.